Okay.
Okay.
So thanks, David. It was nice to see you again. And thank you all for being here. So today I'd like to present you an ongoing project about collective intelligence in chess. And I think if you have any questions, please post them on the chat and I'll answer during the discussion. So what you see here, for instance, this is a movie. This is moving. So that's an exhibition game that we have organized as a preparation for this project. And it's a crowd of about 10,000 people on the internet playing collective chess. So they play with the white pieces against a chess master in black. Okay, and the crowd plays with a majority vote. So for each move, people vote, and the move that is chosen by the largest number is played on the chessboard. And the game continues like that until the end. And we want to know how well the crowd can do that and why. So what are the mechanisms behind that? I was surprised when I started the project because, you know, there's a lot of research about cognition in chess. Herbert Simon, for instance, called chess the drosophilia of cognitive psychology because he wrote, there's so much to learn about the human mind in this domain. And in fact, chess has often been used as a symbol for intelligence. Here, for instance, you have the example during the Cold War, where chess was used as an instrument of propaganda between the Soviet Union and the West world. And that's another example that you know certainly in the domain of artificial intelligence this time. That was 1997 when Garry Kasparov played and lost against a computer, Deep Blue. And so the question is, okay, we know about individual intelligence in chess, artificial intelligence, but how about collective intelligence? Well, surprisingly, we know nothing. Well, collective intelligence and chess, it simply does not exist in the literature. I found one and only one paper that is related to that. And please let me know if I missed something in the literature because I'm really looking for references. But the only paper I could find was a simulation study where researchers made groups of 3 computer programs, not people, programs that play chess. And they showed that the majority of the 3 is stronger than any program taken alone. Okay, so that suggests a form of collective intelligence, but you know, that's all we have so far. So we set up an experimental website and we invited people on social media like Twitter and YouTube. And about 10,000 people signed up to play collective chess for this project. And I will now describe the experimental design and show you the result. We also have a model for that, but I will not talk about the model today for a matter of time. I will just focus on the experiment. Okay, so in the experiment, the participants are playing collectively and they play against a computer. Okay, they play against a computer program. And we use the particular computer program that is called Maya. There's a reference here. That is called Maya, and Maya is a particular program because it's not trying to beat you, it's trying to imitate the human style. So we have an opponent that really plays as a human would do. And we set up 5 different difficulty levels. So for instance, we have Maya 1100, which is easy to beat. And on the other end, we have Maya 1900, which plays like an advanced human player. And we organized 50 games for each difficulty level. And so we can see how often the crowd beats the program in each level, which gives us a good metric to measure collective performance. On top of that, we have another condition. We did a social versus non-social treatment. So in the non-social treatment, people just vote for their preferred move, and the move that has the highest number of votes is played on the chessboard. And in the social condition is exactly the same, but the participants could see on the side the current states of the votes before voting themselves. Okay, so there's a social influence factor that is entering the loop. So that's another experimental treatment. And in the end, we have a simple 5x2 design, 50 games in each category. So that's 500 games in total. All the games were played in parallel at the same time, and participants were randomly assigned to one of the games. Okay, so that's for the experimental design. Here are just some examples. On the left, for instance, you have the first game that ended after only 5 moves, and it was a fast victory for the crowd. The crowd plays in white with the white pieces, so it was a fast victory for the crowd. The final position is shown here, so it's a very simple checkmate. And the last game, the longest one, was a very tight game that the computer eventually won. And this is the final position represented here on the right. So to evaluate the collective performance, we need to know the individual skills for the group members. So we asked participants to rate their chess level on a scale going from 1 to 5. And we got this here, the figure on the left. So participants are mostly beginners and occasional players. And we also asked them to provide their ELO level for those who knew it. And we got this distribution here on the right. So the ELO is the official measure of skill for a chess player. I give you a scale, just to give you an idea. So if you play random moves on the chessboard, your ELO is about 300, okay? Beginners have an ELO of about 800. Occasional players go up to 1300, 1800 for advanced players. If you reach 2300, you're a grandmaster. The current world champion, Magnus Carlsen, has an ELO of 2800. And the best computer program called Stockfish has an ELO of 3300, okay? And the yellow dots here show you the 5 difficulty levels that we have selected for the experiment, so for the opponent. The average ELO value of our crowd, of our participants, is 1165, okay? So on this scale, it's just right here. So that's the average crowd level, 1165. And what is nice with the ELO level is that if you know it, you can derive the winning rate of the 2 players, right? So if you know the ELO of 2 players, you know in advance what's the winning rate if they play one against one another. So if you have an ELO of 1165, that's the average crowd level. If you have that ELO, and if you play against opponents of different levels ranging from 1100 to 1900, then the red zone here is your expected winning rate. There's a formula for that. So you would beat most of the time an opponent that's rated 1100, and you would almost systematically lose against an opponent that is rated 1900. So that's what is expected if the crowd would play at the level of the average group member. Now, the question, of course, is how did the crowd actually perform? Is it better, like above the red zone, or worse, below the red zone? Well, that's what we have observed. So as you can see, it's much better than the expected curve, which let us understand that the crowd plays better than the average group member. The crowd in the experiment has a more than 60% winning rate everywhere, even for an opponent rated 1900. So on average, the crowd is an occasional player, but collectively, the crowd plays like an advanced player. And we also observed that the collective performance is higher in the social condition. So overall, we have 77% winning rate with social information and 64% without social information. Okay, so that's the raw results, the basic results. Now let's try to understand what is happening more precisely. What are the mechanisms behind that? This, for instance, is a position that occurred during the experiment. So the crowd plays with the white pieces, and participants have to make a decision. So what move do you play here? And so I used a chess engine to evaluate the quality of all the possible moves that the white could play here. And the computer says there are, in this position, 22 possible options for the white player presented here, and they're ranked from the best on top to the worst at the bottom. So here, for instance, the best possible move is called H5. So that's basically moving this piece like that. So the computer says this is the best move you could do at that moment. For this position, we have collected 26 votes, and the number of votes is displayed here on the side. So you can see that 15 people have voted for the best move, 6 for the second best, and so on, and 1 person has voted for the worst move at the bottom. Let me represent that with a bar plot. So that's exactly the same data, but now represented as a histogram. So on the x-axis, you have the rank order, and the y-axis is just choice frequency. And now, of course, this is just one move, but let us do that repeatedly for all the moves of all the games in the non-social condition for now. And if you do that for all the moves, you get this distribution, which is interesting. First of all, you can see that even though only 30% of the participants have voted for the best move, they usually get the majority, because the remaining 70%, they tend to spread out over many different options, right? As we say, there's only one way to be right, but there are many ways to be wrong. So all those who did not spot the best move, they actually divide the votes between many suboptimal votes, right? And that explains partly why the majority often points at the best or second best option. The second interesting feature of the distribution is that it's actually a power law, right? And this one has an exponent of 1.18. The exponent of the power law, in this case, is an indicator of the decision quality. A higher exponent means a better decision on average. For instance, we could do the same analysis as a function of the skill level of the participants. Remember, they rated their own level on a scale going from 1 to 5. And we have this very regular pattern here where you see that the line drops faster for better players. We can measure the exponent of the power law for each of those lines, and we get this. So it's a very clean pattern, namely that the exponent increases with the individual skill, right? If I merge all the players together, that's what I've shown before, I got this exponent of 1.18. So that's all the individuals together. Now, if I do the same thing, but just look at the majority decisions, so the collective decisions, I got that, okay? So you see that the decisions of the individuals are equivalent to a level 2 player, that's the exponent 1.18. But the decisions of the majority are equivalent to a level 4.5 player, that's an exponent of 1.7. Okay, so now we have a better understanding of why the majority rule works pretty well, but as usual, things are more complicated than that. So what you see here is a global result, okay, taking all the moves into account together. But on specific occasions, the collective decision can be very bad. Here's an example. That's another position that happened during the experiment. And if you look at it, and if you can play chess, it's actually very tempting to do this. Like there's this unprotected black piece there, and it's really tempting to take it with the rook. And that's indeed what the great majority of people voted for. But turns out it's a terrible move. It has a rank 26 according to the chess engine. And I don't give you the technical details now, but if you do that move, it creates a chain reaction that makes you eventually lose the game. So it's a very bad move that looks good. We call that a wicked choice environment. It's a choice environment in which one option is very tempting, it looks good, but it's actually very bad. And most of the time, the majority falls into the trap. This kind of situation is very rare, but whenever it happens, it's game over, or almost game over. So that means the crowd could be playing even much better if these misleading positions would not occur. Interestingly, if we compare the social and non-social conditions, so that's comparing the blue and the red, you see that for normal decision environments, which we call kind decision environments on the left, there is not much benefit in having social information. So on the y-axis here is the rank of the majority choice. So lower bars means better decisions. And you see that in most of the time, actually, social, non-social doesn't make any difference because the majority already does a good job. However, in this kind of particular wicked choice environment, so whenever you have a trap, then you see that there's a strong benefits for the social environment. So this is in particular the moment where the social information is useful. And the reason why this is happening is actually very subtle. We figured this out just a bit later. This figure shows on the x-axis the voting time, okay? So on the left are those people who voted, on the left are the people who voted first, and on the right-hand side are the people who voted last, okay? So x-axis is the voting time in minutes. And the y-axis is the skill level of the voters. And what you can see is that the better players tend to vote first because the votes are displayed publicly in the social condition, then the players with a lower level who vote later, they actually can benefit from the expertise of the good ones who have voted before, because now it's visible. And this is not useful most of the time, because most of the time the majority is good anyway. But for tricky situations, this is the particular moment where it helps the crowd avoid a bad vote. Okay, I'm gonna skip this last figure and get to the conclusion. So to sum up, there is a form of collective intelligence in chess, and this intelligence is amplified in a social context. We've seen that the majority rule actually does a good job to find out the best move. and that social influence mitigates bad collective decisions in these particular wicked choice environments. And this is made possible because the best players tend to play faster than the less good players. That's it. That's the end of my talk. Thanks for your attention.
Fantastic. And I think we've got lots of questions coming into the chat. You